Good morning, everybody in the lecture hall. Good morning on Zoom, everybody on Zoom. Good morning, everybody binge watching from the future. You're almost done. So today is a special day. As I promised last time, there will be no additional material. I will just wrap up a little bit, remind you of the big picture, that everything we've seen during the semester is actually connected. And I'll tell you a little bit about what to expect at the exam. And after this, we'll have a quiz where I'll ask you plenty of questions. It's a good way to rehearse for the exam and to test your knowledge. Plus, there is a little prize for whoever wins. You will compete against the TA team. So we told the TAs it's in the second hour. So I hope we're going to have a couple of TAs. All right, so let me start with the wrap-up part, and then we'll proceed to the other steps. So I would like to come back to these top 10 design principles of big data that I've actually already mentioned a couple of weeks ago in the middle of the course, and now I would like to go again through them and see that they make sense throughout the entire course. So the first takeaway message, which actually goes beyond big data, is to learn from the past. Because our ancestors did a lot of things. They already discovered a lot of things, but also they made a lot of mistakes. And we can learn from all the mistakes that they made. And concretely, in the context of big data and databases, what they have invented is relational tables, right? That are thousands of years old. As we saw, they are even on some clay tablets from Mesopotamia. And they have also invented just a couple of decades ago data independence, the idea of abstracting away a simple model everybody understands, like rows and columns. Everybody understands rows and columns. And then a few things you can do on it, like project, select, aggregate, and so on, the relational algebra, and the query language. So this is all what our ancestors have built. And it's very tempting sometimes when you want something new to throw it all away and start it from scratch. And this is pretty much what almost happened with messy data, meaning when the data is nested, when the data is heterogeneous, which actually is real life. When you have real world data, it doesn't always fit in relational tables. And then the temptation was big to just throw it all away, what has been done in the relational era, and start from scratch. And actually, fortunately, at some point, people noticed that no, it all makes sense. Data independence, the abstraction, the query languages, everything still makes sense. And so we can use this in order to accelerate the progress of the technology. Another interesting example from learning from the past, or actually maybe failing to learn, is what happened with XML and JSON. Because even though technically JSON predates XML, the development of the XML ecosystem predates that of the JSON ecosystem. So the XML ecosystem is basically under the W3C, the standardization body that also standardizes HTML, XQuery, and so on. And so this ecosystem is very mature. It is so mature that it is used by governments, for example, for the taxis in Switzerland, and in corporate environments. But then at some point, XML is a bit complicated, and JSON appeared, and JSON is actually great, right? It's a great abstraction, even simpler, you could argue, in terms of data model. But here too, the temptation was to just throw away everything that was done in the XML world. And then a couple of years later, people realized that actually we shouldn't. XML schema, now we have JSON schema. XQuery, query languages, now we have plenty of query languages for JSON. So slowly, we just realized actually what our ancestors made for XML just makes sense as well for JSON, right? So perhaps if we would have paid more attention, maybe the development of the JSON ecosystem could have been done even faster. But that's just a few examples of why it's important. And the idea is that tables are not going to disappear, and including the takeaway messages that we got from them. So they are here to stay. But they cohabit with other shapes. that are cubes, trees, graphs, text/vectors, as I said at the beginning. And so in order to deal with this complexity, all of these shapes that are around, we learned in this lecture that we need to keep the design simple. For example, some design that we found in many places throughout the course is key-value pairs. You have a huge collection of key-value pairs. A JSON object is a set of key-value pairs, right? Not huge, because we saw in the document store they cannot be too big, but it's key-value pairs. In HBase, we saw that there are also key-value pairs, right? In the physical storage of HBase. We also saw key-value pairs in XML attributes too. They are also there. We saw key-value pairs in a way in HDFS when we mapped in S3 when we mapped the bucket ID and object IDs, which are the keys, to the values. In HDFS, if you consider that a file name is a key and then a sequence of blocks is a value, then we have key-value pairs as well. And having a simple design makes it much easier to implement, but it also makes it much easier to optimize, and it also makes it much easier for people to understand how that works, right? Key values are very, very easy to understand. Even in real life, right? Everybody in Switzerland has a social security number, and in many countries throughout the world, and you can also see it as a key value model where the social security number acts as a key. I like this quote by Albert Einstein that everything should be as simple as possible, but not simpler, because if you go beyond the, let's call it the entropy of what you're building, if you go below that, then at some point it doesn't work anymore. But still, there's a beauty in the simplicity, also in science in general. And physicists also like to have beautiful formulas, you know, that often is a sign that a theory makes sense. Then we have number 3, which is the modularization of the architecture. It's just like when you build a home. There are people who prepare the ground. There are people who build the walls, electricity, plumbing, and so on. It's different people. So there's a modularization. And the same happens in computer science. We also design the system in modules. And in the case of big data, we saw that we have libraries that are good at storing stuff. We have libraries that are good at modeling stuff. Some others that are good at validating the structure of the data. Some others that are good at querying the data and so on. And it's just organized nicely in modules that communicate with each other, but in a very nice vertical fashion. The data shapes, actually, thanks to this modular structure, the data shapes that I showed earlier have something in common, and that, again, has to do with learning from the past. They have a paradigm, a data model, a syntax, a query language, an architecture for the systems that implement them, and they also map to other shapes. For example, if you look at the 5 shapes, cubes can be sliced, diced, aggregated, rolled up, pivoted, cross-tabulated, and so on. That's not part, don't worry, it's not part of big data for engineers, so don't be scared, but you can do that with cubes. In tables, you can select, project, rename, and so on. In trees, you can look up, navigate, normalize, denormalize, validate. Oh, I already said, no, I didn't. Navigate, validate, select, project, group, and so on. For graphs, you can traverse, you can find patterns, and so on. Don't worry, graphs are not part of big data for engineers either. And vectors, which also are not part of big data for engineers, you can compute scalar products, you can compute the distance between vectors, you can transform or use the transformer architecture. It's basically beautiful linear algebra. So you see, they all have this in common. They have a paradigm, a model, and then you can do things with them. You have some sort of algebra. In this lecture, we focused on tables and trees, right? Just to be clear. And then what they have in common too is syntax. When you have a cube, you can serialize it. So when you create some text or binary file from something in memory, it's called serializing, right? The opposite is called parsing. So you can serialize cubes as XBRL, which is the format used by many governments and agencies around the world. Tables can be serialized as CSV, right? You know, when you go to the Federal Statistics Office or plenty of these places where you can download data, CSV is very often available, but XML and JSON as well for trees. And then you have binary formats also, like BSON that's used by MongoDB, but it's hidden from you, so you don't actually see it. Then we have Parquet, Avro, Protobuf. So what these formats have in particular is that they are very efficient, because in Parquet Avro protocol buffers, you have schemas, right? You have a schema, the data is structured according to that schema, and that means that the place you need to save the data is much smaller. So the memory footprint of this format is much smaller. You can read them faster. It's very, very efficient, right? XML, JSON, BSON would take more space because you don't have a schema necessarily. Then we have graphs. In graphs, you can serialize as RDF, RDF over XML, Turtle, and so on. There's many formats to serialize graphs. And vectors, maybe you've heard, but actually vectors these days can be serialized as normal text, because in fact, when you use ChatGPT or a chatbot, what's actually happening behind the scenes is that you have vectors embedded, so the words are embedded in some vector space. And this is actually why I said here, you compute scalar products and so on. This is actually what happens. When you use ChatGPT and so on, you type text, you get text as an answer, but actually what's going on is linear algebra in the background. And then how do you query this? You also have languages. So cubes, you have MDX, which you don't know again because it's not part of the lecture. Tables, you have SQL, this one you know. For trees, you have JSONic, which we covered in the lecture. XQuery would be the same, but for XML, standardized by the W3C. AQL, nickel, uncle, particle, GraphQL, I'd say a word about that. The market has not consolidated yet, but hopefully it happens someday. For graphs, we have a GQL, Cypher, SQL over PGQ, Sparkle, and so on. Very good news. For graphs, the market has now consolidated because the vendors have managed to agree on some common query language. And now they are all migrating their software to comply with this standard that they have agreed with. So this is very, very good news, and hopefully inspiring for the people developing tree-based systems. And vectors, well, by chatting or talking with it, right? You just type some words and you get some words as an answer. That's basically the query language, right? Even via voice. The next point is that we saw is homogeneity in the large. When you want to store petabytes of data, exabytes of data, in order for it to remain manageable, you want some homogeneity at the very large scales. For example, in HDFS, you have just plenty of blocks. In S3, you have plenty of objects. In tables, you have plenty of rows. In wide column stores, you have plenty of columns and plenty of rows and so on. So you have some homogeneity in the large because you want to solve that problem. Right, we saw that the quantity of data we can store has increased absolutely massively in the past decades. But now the problem we have is we cannot read it fast enough in comparison to the quantity of data, right? We can read faster, but not as faster as the quantity of data we save, right? So if you look at the increase of the throughput, it's actually ridiculous, 40K compared to 91 billion. And so this is why we need the homogeneity in the large, because that allows us to nicely partition the data in order to deal with this. And when you partition the data, you can parallelize it nicely over machines, right? So this is what we call scale out. When you buy plenty of cheap machines and then you have all of these blocks or chunks or splits or shards or all these words that we've seen, partitions, that you can spread all over the machines, and that solves this problem right here, right? So that's why homogeneity in the large is actually very useful. But because the data might be highly nested and heterogeneous, and because this is the real world, right? In the real world, data is just not structured in relational tables, fortunately, actually. And so it's all heterogeneous, but that's absolutely no problem for big data systems. If you think of document stores, you can have collections of JSON documents or collection of XML documents in XML document stores, and they don't need to be validated, right? And again, that's handled efficiently with the homogeneity in the large, because you just see it as a collection of documents, right? And you look at the documents like black boxes that you don't look inside when you store them. All right, so that's heterogeneity in the small. Then you have the nestedness, the fact that when you denormalize the data, you can have tables in tables in tables in tables, like the Inception movie, and you end up with collections of trees, which are the generalization of tables. We saw that in order to validate this and check, for example, that in the same column we have the same kind of data, we have type systems. At first, it looks very daunting, just to me, like when I arrived in Switzerland and I discovered Baseldeutsch, Zürichdeutsch, Ostschweizerdeutsch, Berndeutsch, Walliserdeutsch, and that's pretty much the same here. We have plenty of dialects. Every piece of software has their own set of types. But if you actually look at them, they're pretty much all the same. Right? They might not exactly call them the same. Some might implement some types, some others, some other types, but actually they're the same. And so you need to zoom out and see the big picture here. It's pretty much always the same types, and it all comes down to reading the documentation for the system you are going to learn and see what they are called and what is supported, right? So don't forget to zoom out on the types. Just don't have your eyes on a specific system, you know, and that it's really the big picture here that matters. And we saw also that there's atomic types, ones you have at the leaves of the trees that are atomic. And then we have object arrays, like all of these structured types that are recursively made of further components, right? And this is what enables the nesting, the objects and the arrays. Then we saw that also to enable the data in the small, we can serialize the data to text as XML, JSON, and so on. But we can also validate it with XML schema, JSON schema, and so on. We can store it efficiently, Parquet Avro. We can query it with XQuery. So that's a whole ecosystem that was built to do with that data in what we can do with tables. The next item is the abstraction of logical models from the physical implementation. That is data independence. Very, very important. That's how you keep your sanity. This is exactly why you can have people without a computer science background use these systems without needing to learn C++ or Java. Right? You just sit in front of a Jupyter notebook, type your queries, SQL, JSONic, and you just let the computer worry about all the rest, right? So this is the idea of this abstraction, but it's fundamental for computer scientists, because what that means is that then, without modifying the user's behavior or what the users know, the engineers that design the system can completely re-implement it without the users noticing. They will notice it's faster, but they will not notice any change in the way they use the system. So this is why it's so important. Speaking of data independence, actually, the shapes can be mapped on top of each other. So you can actually store cubes as tables that we saw in information system for engineers. Tables can be also stored as trees, because we saw that tables are basically just homogeneous collections of flat trees, right? So you can store a table as a collection of trees. Trees can be stored as graphs easily, because trees are basically graphs without cycles. Graphs can be stored as tables. That's what we see in the masters with the computer scientists, but you can store the edges and the nodes of the graphs in tables. And text can also be stored actually for the vectors. You have extensions that allow you to store the vectors in tables, for example, in PostgreSQL. It doesn't mean it's going to be efficient, but it can be done. So whenever you implement some data shape for the first time, it's very common to abuse another system by mapping, and later have a better implementation that directly implements it. So what we call a native implementation. So the evolution of the architecture in general goes in that direction, that you have the storage completely hidden, like Bison in MongoDB, nobody looks at it. Then you have some system like MapReduce or Spark in the middle, but also ideally in the future hidden, that people don't also see that anymore. Then you just have a fancy declarative language on top of this that makes it easy and straightforward for people to communicate with. And so this is the evolution. You can look at software engineering, databases, and machine learning separately, but there has been this evolution from low-level languages like assembly codes that you might have heard of that evolved into higher-level languages. You can see Spark or MapReduce as the assembly code of databases or the MongoDB API as assembly code. And then you have the higher level query languages like SQL and so on. And the same in machine learning, even though it's taking a bit more time because this is more recent. But you can see PyTorch, TensorFlow, and so on as the assembly code of machine learning. And there are people working on high-level languages for machine learning, where you just declare what you want to learn with very few lines, and the system takes care of everything. Very, very challenging because in machine learning, so you have a lot of parameters, hyperparameters to tune and so on. So it's absolutely not trivial to get it right. But still, there are people working on declarative machine learning. RumbleDB is actually meant to show that you can use a language, like in that case, JSONic. And below, hidden, we have Spark, HDFS, S3, the local file system, and so on. Then we saw that's also because of the homogeneity in the large, we can shard the data, spread it all over the cluster. We can also replicate the data by storing it multiple times. So every partition gets stored on multiple machines. That's how we make sure that if it crashes, we don't lose the data. For that, we buy a lot of cheap hardware, plenty of machines that are rather small, but thousands or tens of thousands of them. Or even if you are a very large company, millions, tens of millions of machines, if you have even plenty of data centers that each have tens of thousands of computers, right? And the decentralized architecture is very common, doesn't have to be. We also have, that's not covered in this lecture, but we see in the master's lecture, DynamoDB by Amazon, that's a key value store. This one is actually decentralized. But for everything we saw here, HDFS, MapReduce, Spark, HBase, Yarn, and so on, it's all using this centralized architecture, which is not without problems, but there's bottlenecks and issues, but we saw how they can be circumvented. And the point number 10, it's the batch processing. It's the idea that when you have trillions of records, you just cannot process them one by one. Because if you would compute what it would take, like if you spend 1 second in every record that there is among a trillion or a quadrillion records, you will quickly notice that it would take basically the age of the universe to process this. So it just doesn't work because of latency, because of the time it takes to go from one to the other. So what you do is you batch process. Instead of doing them one by one, you do them 100,000 by 100,000. Right? And when you do 100,000, it's just a for loop on a machine that's very quick. And then you proceed to the next batch of 100,000 with a small cost for the context switch. But if you batch them in these very large groups, then you have less context switches. That's also an advice for real life, right? When you work or you have a job in a company, now we tend to be distracted by the smartphones that just keeps beeping with alerts and so on. But in fact, this is bad for us because it makes us context switch. It keeps changing our attention to something else. But the secret for productivity is the ability to focus on something for an extended period of time, like 1 hour, 2 hours, and then you move on to something else that actually is less tiring for the brain, also because of latency and switching to another context. So this is also wisdom that goes beyond big data. All right, so now what's going to happen for you? You're going to have projects, maybe semester projects, master's thesis, where you analyze data, you might work in company, and now you're equipped with the knowledge. You will be able to learn existing products, even if they are not part of the material. Now you have the basics, like learning new types, learning a new language, and so on. Should not be a problem for you. You can also choose which product to use. If you're asked, like you have a specific use case, a certain size of the data, a certain shape, and so on, now you can pick the product based on the high-level knowledge you have now. And for some people, but maybe rarer, you might even design whole new products or technologies, right? If you even notice that you came to the limits of what already exists, then maybe you can design something new. And so in order to make these choices or to learn new products, you always have to come back to the basics. Ask yourself, what is the shape of the data? Is it tables, cubes, trees, graphs, vectors? So you have to ask yourself that. How much data do you need to store? Are you just talking about a few megabytes or gigabytes? Probably fits on your laptop. Or are you talking about terabytes, petabytes, exabytes, and then you need a data center, right? That's in fact something that is especially important for startups. For the maybe some of you are going to found your startup, and then you have to ask yourself the question of the resources that you need, right? The computers and so on. And so there is a mistake that is commonly made. It's to think that you need several machines when in fact you could just fit it all on one machine. Of course, then you have to sit, you have to figure out how do we optimize the format and the code to fit it on one machine. But in many cases, you can do it with a single machine, right? So if you go on multiple machines, you need to know why. There is one little exception where being future ready for multiple machines is for a startup is that you don't know how many people are going to use your system, but if suddenly it goes viral and suddenly many people use your system, it's still a good idea to have a setup in the cloud that is ready to scale, that you just push a button, then you have more machines. But it doesn't mean for this that you need to have a system that uses multiple machines for a single query. It's only a matter of duplicating the environment easily. All right. And then, of course, what you want to do with your data. Do you want to query? Do you want to do selection, projection, aggregation? These are very different, right, in the way you want to use the data. So all of that plays a role, but you really need to ask yourself before you invent something new, are you reinventing the wheel? Are you not trying to solve a problem that people have already solved? So it's always a good idea to go to a search engine or a chatbot. Some of them work well, and ask if that's not already been invented. Then you can just go ahead and reuse it and save yourself a lot of resources. And again, that's I'm repeating, but always ask yourself, do you really need more than one machine to do what you are doing? And also maybe the sibling question to that one, do you really need MongoDB or MapReduce or Spark? Because in many cases, all you need is a relational database. Right? Many people just need PostgreSQL or relational database. You also need to ask yourself that, do I really need data that is nested and heterogeneous? Sometimes yes, sometimes no. So always a good question to ask. So that's to remind you of what happened with big data weights made of all the technologies we've learned. It's really just because the way that things have evolved in the past decades with the data we create, how fast we read it, and the latency got out of control. And so we needed to invent these technologies to accommodate for this discrepancy. So what's going to happen in the future? I don't know, but it's getting closer because I started that maybe 10 years ago, and now some of this actually has happened. MapReduce or Spark becoming invisible, that's kind of happening. There's Spark SQL now. There are more and more people who realize that you need these higher level architectures and shield the user from the complexity. Hopefully, this is something that is taking some time and pedagogy. The fact that data shapes are important. If you have your data in a certain shape and you try to store it and query it with a system that is built for another shape, two things are going to happen. First, you're going to not be productive because you're going to try to write queries for the wrong shape. That's going to eat a lot of your time. And the second thing that's going to happen is that when you try to run your query, it's going to be super slow. So this is why the shapes are so important, and to really ask yourself, what's the shape of my data, and to find the right product that has the right shape. Querying all data shapes will be standardized. This is ongoing. Tables is already done. Graphs, as I said, it's been done just recently, that now we have this standard and the vendors are migrating to it. Now the big problem is for the trees, but hopefully, as I said, this will happen. I like this comics. It's an XKCD, where you have a situation. Who knows this one? situation, you have 14 competing standards. That's actually pretty much the case, even though it's beyond 14 now, probably at 30 or 40 by now, all the languages that exist for querying JSON-like data. And then people figure out that, oh, we need a language, or the existing language are not good enough, or there's too many languages. Let's unify them and invent something new. And then you end up with fancy websites, like there's plenty of them that basically say, oh, now we have this new query language and so on. And the situation is that you've just added one more language. So that's every couple of months, there's new announcements. XQuery, I would say, was the first one because that's W3C. JSONic came shortly after that for JSON. That was maybe 2010, 2011. As part of the discussion, actually, in the XQuery working group when you discussed JSON support, the reaction back then was interesting because the reaction we got was, first, why do we need a query language for JSON, which back then people didn't get. Today, they get it so much that there's 30 of them, but back then people didn't get it. And another reaction, like, we have JavaScript already, right? Because JSON, J is for JavaScript. So why do we need a language? Because you can use JavaScript. But here, they miss the point that JavaScript is not a query language. It's an imperative language like C or Python, but it's not a functional declarative language. So yes, I like to show this comic right here. I'm trying to keep track of all the languages that pop up every couple of months. But you don't have to worry, because if you look at them, they really follow the same principles. So if you have to learn one of them for a specific product, since you've already learned JSONic, you will see the principles are going to be very, very similar. You know, JSONic and SQL, by the way. All right. Then we'll have more and more UIs. For many people, you might have heard of even this hype of no code, right? That you don't even need to write any code anymore for building systems. Can be debated, but it's actually, in some cases, it actually works. Even better than that, we will talk to our databases, and now I should remove the future and put the present on it, because this is now what we are actually doing. We can literally write and ask for something, and it comes back, and we just discuss in English or even our mother tongue with the system. So this is one of the examples of something that now we can consider has happened. Another aspect is something that it's more like an idea that I call data fungibility. You know that something like water or electricity can be considered fungible, right? When you buy water, let's say a similar brand or quality, it doesn't matter which molecules of water you have, right? You buy a bottle of water or another one of the same brand, it's interchangeable, right? That's fungible. You can even pour water from a glass to another glass, from a bottle to a glass, and so on. Electricity is the same. When you purchase electricity, you have the option in Zurich, of course, of selecting the source of the electricity to influence the way it is produced. But what is nice is that the way it comes to your home, it's just electrons, right? And it doesn't matter if it's this electron or that electron that is moving to your home, right? In fact, the electrons aren't moving so much because it's alternating current, but you get the idea, right? When you have electricity, when you consume it, it doesn't matter how it was produced. And this is why electric cars actually are such a big deal. It's really about the decoupling of the consumption from the production. Now you can change the way you produce the electricity without changing the engine of the car. And that's actually the same as data independence, if you so you can see the same principles in there. And so the fungibility, you can see it a little bit when we have the idea of the blocks. First, you see some fungibility here, but there are two formats in particular, two data shapes where this is true. It's graphs, RDF, where you have collections of edges in a graph, and you have cubes where you have these huge collections of cells. So I would say that the cubes and the graphs are data at the highest fungibility level, but just a general idea regarding this. Then you know that data and money tends to be converging. It's a very slow process. It's also a debate of whether it will happen, if it's not going to happen, and so on. But basically, this is all about the evolution of transactions between people, right, over thousands and thousands of years, and how you do the record keeping of who has what, right? And so if you think of it, it's a data problem, it's a database problem. So we solved it back then with banknotes and coins, gold coins and so on. And now this is going into computer science, cryptography, and distributed systems to solve all of these problems. Yeah, this is not to be taken as an advertisement to buy anything. This is only about the technological aspects of the problems that the blockchain is solving. Then we have the notion of data protection, that just because we know how to query data doesn't mean that we should just abuse it. And so in the EU, for example, it's a topic that is on everybody's minds with data protection. That's the GDPR that happened already a couple of years ago now. We'll see how it evolves and how much control people retain over their data. But this is also an important topic. It also determines when you use data centers as a company, you have to be careful about where it is. Because at first you might think, okay, I'm just putting it all over the planet or I diversify and so on. But if you are, for example, a bank, it's not so easy. You cannot just be a Swiss bank and then store the data on the other side of the planet, right? There's laws that say where it's authorized to be stored. And so this is a very current topic. And now you see plenty of companies like Amazon, Google, and so on that are basically really building data centers right here, creating subsidiaries. And so it means that even though you get all of these nice features of data centers and replication, you still have to respect the law where you store the data and what you do with it, right? So this is also something to keep in mind. There are courses at ETH about this. One is called the Big Data Law and Policy. That is a guest course that I can recommend. Yeah, so basically, you know, like in Spider-Man, right? Great power comes with great responsibility. Then we have something interesting going on between machine learning and database researchers, which there's two schools of thoughts. There are the researchers who think that machine learning is going to leverage cutting-edge database technologies, meaning that we can run machine learning on top of existing frameworks. An example of that is SparkML, which allows you to run machine learning on top of Spark. But interestingly, there are people who think the reverse, that it's the database technologies that are going to be running on machine learning. And an example of that, that's a former colleague of mine who did his PhD at ETH, now at MIT, and they are replacing the indices, so the B+ trees, the hash indices that I've shown you for MongoDB. They're just replacing it with machine learning. Instead of having a B+ tree or a hash table, you just replace it with a model that predicts where the data is to be found. And it seems to be working. And so their ambition is to not stop here, but replace all of the components of the database system with AI and machine learning everywhere. So we'll see if that works or not. But this versus this is actually pretty funny to observe. Who is going to eat whom between ML and the databases. Quantum computing is also very interesting, even though now for databases it's very early, even though there are people who work on the quantum version of JSON objects and JSON arrays. So quantum maps, quantum lists, and so on. So it's actually something that is being born. Who knows about quantum computing? Who doesn't know about quantum computing? So I can maybe say on the very high level what they change. So I will be, of course, oversimplifying because it would take more time to go into details. But basically, in a classical computer, you have a bit that is a 0 or 1, right? It's either a 0 or it is a 1. In a quantum computer, you have qubits, and a qubit is a superposition of 0 or 1, right? So it's not determined. If you want to know if it's a 0 or 1, you have to measure it. It's a measurement, and then it decides if it's 0 or 1. But in a way, as it commonly admitted today, is unpredictable, right? You basically have a probability distribution. And so what happens when you use a quantum computer to solve problems is that it's working on a superposition of data. So you have all the data that you have, but as qubits superposed, and you're kind of computing everything in parallel on everything that the data can be. And then at the end, you get the results. But there's two catches. The first catch is that even though it seems that you're computing something in parallel, and not in parallel like on a cluster, in parallel at the same place, like literally on the same computer, you will only get one result for one piece of data. You're not going to get the results for everything that's been done in parallel, only one. That's the first catch. And the second catch is that you don't get to pick which one. So it's like it's processing things in parallel, then it gets a result, but it decides for you which results you are going to get. So it's highly probabilistic, difficult to predict. But because of some interference that happens when you compute everything in parallel, there's interference patterns, and that is going to somehow lead to a higher power in terms of algorithmic complexity. So for example, you can factor integers into prime numbers much faster by orders of complexity than you can do with classical computers, right? So this is basically what quantum computers are about. And right now, it's too early to say how it will interact with databases. There are now people trying to work on operating systems for quantum computers. There are people working on programming languages, but more like imperative ones for quantum computers. And so I don't know, maybe in 10, 15, 20 years, maybe we'll also have database systems and query languages for quantum computers. If we can build them, because this is a third catch, is that we don't know if this is going to work. We keep building computers with more and more qubits, but the problem is that we don't know if at some point things will just break, in the sense that we'll hit a wall and we just cannot build bigger computers. Right, but it's a very big topic at the moment. And it turns out that there are many links between relational database systems and quantum physics. So there's a bit of literature around that is actually very interesting to read, right? Because you can consider when you have these either the superpositions or the distributions over, let's say, possible data sets, you could view it, to simplify, as a relational table where you have a probability distribution over the rows of the table, kind of. All right, but this is much beyond the material of the lecture, just about what could happen in the next decades. And then this is like completely, maybe even thousands of years or millions of years, but this is all the big question about the evolution of the universe. So there is a bit of a paradox that we have. So if you know a bit of thermodynamics, there's the second principle with entropy. It basically says that it's easier to destroy than to create. So for example, here the molecules of oxygen and nitrogen and so on is spread all over the room. And the probability that suddenly they will all be in that half and none in here, you can forget about it. It's basically close to zero, right? This is just the second principle of thermodynamics. And if you look at the universe, so the second law says that we should evolve towards increasing entropy. And what we observe around us is the opposite of that, like on Earth. Because if you look around, we build stuff, we give structure, everything is becoming more and more structured with time. And that seems to contradict the second law of thermodynamics. And then it's interesting to ask what's going to happen later if we start to go into space and so on, and keep building and building and building. And at some point you have robots that keep building. So are we just basically turning the entire universe into a database in a way when we do that, right? So interesting thoughts to have about these things, but maybe more on a philosophical level. So now we are going to have the break soon, but right now we have a few TAs, I think, who have joined us. Maybe you can come to the front just to get an applause. Come to the front. So we have Christopher, Luca, and Zikai. Do we have any TAs on Zoom? Let me quickly look. All right. So please, big applause for the TA team. So in the second hour, we are going to play. So you're going to play against the students, going to play against the TAs. Thank you for the wonderful job that you've been doing. But winning against the students, that is much more complicated to do that. The students have won a lot against the TAs in the past. All right, but it's fun. That's the whole point of it. So you can see it if you want. You don't have to say we'll have a break, 15 minutes and so on, and then we'll play. After the break, because I'm going to let you go after the break, I'll say a few words on the exam, and right after that, we'll have the big quiz. So see you in 15 minutes, quarter past 9.